How do roads survive desert temperatures above 50 degrees Celsius? What if the very road you are driving on could start melting under your tires? How can pavements survive when surface temperatures soar beyond 70 degrees Celsius in the world's hottest deserts? Why does bitumen, the black glue that binds asphalt, begin to soften in the heat? And how do engineers stop shifting sands and sudden flash floods from swallowing entire highways? You are watching episode 2 of our special series on road construction in extreme climates. This episode takes you deep into the deserts, places like Saudi Arabia, Oman, the United Arab Emirates, Namibia, Rajasthan, Australia, Mexico, and the Nevada Desert in the United States, regions where the climate pushes both materials and design to their absolute limits. The links to the other episodes in this series are given in the description. Check them out to learn about the unique challenges and solutions for building roads in flood-prone regions, cold climates, and high-altitude terrains. So what will you learn in this episode? We'll uncover the unique challenges of desert highways, from heat that softens bitumen to flash floods that rip through dry riverbeds. Then we'll go layer by layer through the construction of a desert road. Starting with the subgrade, moving through the granular subbase and base course, then to the binder course, and finally the wearing course, the road's first line of defense against UV, sandstorms, and extreme heat. After that, we'll look at sand and flood protection measures, explore modern technologies like solar reflective coatings and plastic-modified asphalt, and finally review maintenance practices and real-world case studies from across the globe. So let's begin our journey into one of the toughest engineering challenges on Earth, how to build roads under the burning desert sun. Welcome to Civil Guru, where we bring civil engineering to life in multiple languages, including English, Spanish, French, Portuguese, Arabic, Hindi, and Tamil. Please select your desired language from the playlist or from links given in description. If you find this video helpful, please like, share, comment, and subscribe to our channel. And if you'd like to support our work, you can now contribute through Super Thanks. Even a small gesture makes a big difference and helps us create more high-quality educational content. Thank you. What makes desert road construction so challenging? Why is it so difficult to build and maintain roads in deserts? The problems go far beyond heat alone. In desert regions, roads must fight against extreme temperature swings, shifting sands, water scarcity, and sudden flash floods. Each of these creates unique challenges for engineers. Let's break them down one by one. Extreme temperature swings. One of the biggest issues is with bitumen, also called asphalt binder. Bitumen is the black sticky material that holds road aggregates together. At very high temperatures, especially above 55 degrees Celsius, weaker grades like VG30 start to soften. When this happens, roads experience rutting and bleeding. Rutting means permanent depressions form in the wheel paths. Bleeding means excess bitumen rises to the surface, creating a shiny, slippery layer. A desert road must resist heat not for a day, but for decades. Otherwise, it begins to fail almost immediately. Shifting sands. Another challenge is wind-blown sand. Sandstorms constantly sweep across highways, burying sections of pavement. This doesn't just look dramatic. It is deadly for roads. A single sandstorm can bury a highway overnight, covering markings, reducing skid resistance, and making driving unsafe. That's why engineers must design not just the road, but also the defenses against moving sand. Water scarcity. Then comes the issue of water. Compaction of soil and curing of concrete both require water, but deserts have almost none to spare. Engineers often transport water from far away or rely on chemical alternatives. Without this, the very foundation of the road cannot form. In deserts, a lack of water can stall construction for weeks, or worse, lead to weak foundations that fail under the first wave of traffic floods. And finally, although deserts are dry most of the year, they are prone to sudden flash floods in dry riverbeds, locally called wadis. These floods arrive without warning. Heavy rain may fall in distant mountains, and within hours, walls of water crash through the valleys. One flash flood can destroy months of construction in just a few hours, washing away embankments, eroding base layers, and even cutting highways in half. Because of all these factors, international standards like the Indian Roads Congress, IRC, and the American Association of State Highway and Transportation Officials, AASHTO, classify deserts as a separate climate zone. These codes recommend using special binders with softening points above 55 degrees Celsius to handle the heat. So, desert road construction isn't just about laying asphalt on sand. It is about fighting the elements: heat, sand, water, and sudden storms, all at once. And before engineers can fight the desert above the ground, they must first prepare what lies beneath. The battle truly begins with the subgrade, the foundation of every desert road. Layer 1. Subgrade. What lies beneath the desert road? What if the strength of a desert highway was not decided by asphalt or concrete, but by the invisible soil buried a meter beneath your tires? That hidden layer is called the subgrade, the natural soil foundation on which every other layer rests. If the subgrade fails, the entire road fails. In deserts, the natural soil is usually dry, loose, and sandy. It has very low strength and poor load-bearing capacity. In fact, its California bearing ratio, or CBR, is often below 5%. The CBR test measures how much load soil can carry compared to crushed stone. A higher CBR means stronger soil, depth, and compaction. After clearing away vegetation and organic topsoil, engineers prepare the subgrade to a depth of 90 centimeters to 1.2 meters, depending on the traffic and design. This depth isn't compacted all at once. Instead, it is built in layers of 200 to 250 millimeters, meaning the subgrade is compacted in about 4 to 5 lifts. What materials are suitable? Not every soil qualifies for subgrade. Engineers check the plasticity index, PEI, which tells us how much the soil changes shape when water is added. If the PEI is less than 3%, the soil is too sandy, with almost no cohesion. It crumbles under load. If the PEI is greater than 6%, the soil behaves like clay. Clay expands when wet and shrinks when dry, making it highly unstable. That's why the recommended PEI for subgrade soils is between 3% and 6%. It's the sweet spot, sandy enough to avoid swelling, but cohesive enough to hold together. Optimum moisture content, OMC. Compaction works only if the soil has the right amount of water, called the optimum moisture content, or OMC. For desert soils with PEI between 3% and 6%, the OMC is typically 8% to 12%. If the soil is too dry, particles don't bond, and compaction is weak. If it's too wet, water fills the pores, reducing strength. That is why in deserts, water tankers or even recycled wastewater are used to bring the soil to its OMC before rolling. Stabilization of weak desert soils. But what happens if the soil doesn't meet PEI or OMC requirements? Engineers strengthen it through stabilization techniques. Mechanical stabilization means mixing the soil with gravel, crushed stone, or coarse sand. This improves density and load-bearing strength. Chemical stabilization involves adding 2 to 6% cement or 1 to 2% lime. Both act like glue, binding particles together. In modern projects, enzyme-based stabilizers or bitumen emulsions are sprayed on the soil to reduce dust and improve bonding. And when the soil is extremely loose, engineers use geosynthetics like geogrids, geotextiles, or geocells. Think of them as reinforcement nets that hold the sand in place and stop it from shifting. Target strength. According to IRC and AASHTO standards, the finished subgrade must reach a minimum CBR of 10%. Only then can it safely carry the loads from all the layers above. So the battle against the desert doesn't start with asphalt. It starts here, underground, by carefully checking the PEI, OMC, and CBR, and by stabilizing weak soils, engineers turn loose desert sand into a reliable foundation. But once the foundation is stable, the next challenge begins. How to spread the heavy traffic loads without overstressing the soil beneath? That's the role of the sub-base layer, the protective blanket that comes next. Layer 2. Subbase. How is load spread in weak desert soil? If the subgrade is the hidden foundation of a desert road, the subbase is like its protective blanket. Its job is simple but vital, to spread the weight of heavy traffic across a wider area so the weak desert soil beneath is not overstressed. In desert highways, this subbase is usually made of granular subbase, or GSB, a carefully blended mix of coarse aggregates, smaller fines, and sometimes a bit of soil. The largest aggregates in GSB are about 75 millimeters, while the finer part includes sand, quarry dust, or soil. The key detail here is the fines content, which must be about 8 to 12%. Why is that important? Because those fines act like tiny wedges, filling the gaps between bigger stones and locking the entire layer together. If there are too few fines, the layer remains loose and unstable. If there are too many fines, more than 15%, the layer starts behaving like clay. It traps water, loses strength, and quickly fails. So the right balance of coarse aggregates and fines is what makes GSB strong. Thickness in desert roads. In deserts, where soils are weaker and more prone to expansion and contraction, engineers make the subbase 25 to 30% thicker than in moderate climates. That usually means a thickness of 200 to 300 millimeters, depending on soil strength and traffic load. Both IRC 37 and AASHTO recommend these thicknesses, with adjustments made for highways carrying heavier traffic. Optimum moisture content, OMC. Even though the subbase looks like coarse gravel, it still needs water for proper compaction. The optimum moisture content, or OMC, is usually between 6 and 9%. If the water content is too low, the particles don't lock well, and the layer stays loose. If it's too high, water fills the voids, weakening the structure. That's why engineers spray just the right amount of water while rolling to achieve maximum density. Strength requirement, CBR value. The performance of the subbase is measured again using the California Bearing Ratio, or CBR test. Here, the minimum required CBR is 20 to 30%. Well-graded GSB often achieves CBR values above 50%, and if it's treated with cement or bitumen, it can even rise above 80%. That level of strength ensures that the subbase can handle the loads from trucks and buses without transferring stress to the weaker subgrade below. Special practices in desert roads. But deserts always bring unique challenges. The biggest one here is water scarcity. Even this layer needs water for compaction, but deserts don't have enough. So engineers often rely on water tankers, or even treated wastewater. In some international projects, a small amount of bitumen emulsion is mixed into the subbase. This helps bind the particles, control dust, and reduce the need for excessive water. So the subbase is not just a random gravel layer. It is a carefully graded, moisture-controlled, and strength-tested blanket that protects the foundation below. But while the subbase spreads the load, it is not enough on its own. Roads still need a backbone, a structural layer strong enough to carry millions of wheel loads over years. That's the role of the base course, which we'll explore next. Layer 3. Base course. What adds structural strength to the road? If the subgrade is the foundation, and the subbase is the protective blanket, then the base course is truly the backbone of the pavement. This is the layer that carries the heavy traffic loads and gives the entire road its structural strength. Without a strong base course, the layers above will quickly deform, no matter how well they are designed. Wet mix macadam, WMM, the standard base. The most common base material is wet mix macadam, or WMM. This is a mix of crushed coarse aggregates, smaller fines, and water, blended in a plant and then laid on site. The largest aggregate size is about 40 millimeters, with a well-graded distribution down to very fine particles that pass the 75 micron sieve. About 8 to 12% of the total mix is made up of these finer materials. Their role is crucial. They fill the voids between larger stones, locking the structure tightly. The WMM layer in desert highways is typically 150 to 200 millimeters thick. To achieve maximum density, It is compacted at its optimum moisture content, or OMC, which for WMM is about 4 to 7%, lower than the subbase, because the material is denser and has less void space. When compacted properly with vibratory rollers, a WMM base can reach a CBR value of 80 to 100%, making it nearly as strong as crushed stone itself. Cement-treated base, CTB, extra strength when needed. For highways that carry very heavy traffic, engineers often upgrade to cement-treated base, or CTB. Here, 3 to 5% cement is mixed into the aggregate blend. The cement acts like glue, binding the particles and turning the layer into a semi-rigid slab. This significantly increases strength. A CTB layer can reach CBR values above 150%. CTB is especially useful in freight corridors and desert expressways, where trucks and trailers apply repeated heavy loads. Bitumen stabilized base and foamed bitumen, high-performance options. In modern projects, engineers sometimes use bitumen stabilized bases. Here, 2 to 3% bitumen is mixed with aggregates, but building the base course in deserts comes with its own challenges. Under the desert sun, water evaporates quickly, making compaction difficult. To avoid this, engineers schedule construction early in the morning or after 5 p.m., when temperatures are lower and winds are calmer. In some cases, water-retaining additives are also used to reduce evaporation during compaction. So the base course is not just another gravel layer. It is a densely graded, carefully compacted, and sometimes cement or bitumen-stabilized backbone that gives desert highways their long-term strength. But even a strong backbone needs protection. The next question is, how do we prevent the asphalt layers above from softening and rutting in desert heat? That's where the binder course comes in. Layer 4. Binder course. How does the road resist high-temperature rutting? By now, the desert road has a solid foundation, a stable subgrade, a protective subbase, and a strong backbone in the base course. But we're not done yet. The next layer is where the pavement first meets bitumen, and in the desert, this layer faces its greatest enemy, extreme heat. The binder course, also called the intermediate layer, is the first asphalt shield. Its job is to bind the lower structural layers together and prepare a stable platform for the final surface, the wearing course. The prime coat, bonding the layers. Before the binder course can be laid, engineers apply a prime coat on top of the base course. This is a thin layer of cut-back bitumen, like MC30, or more commonly today, bitumen emulsion, sprayed at about 1.0 kg per square meter. The surface is then left to cure for at least 24 hours. Why is this important? Because the prime coat penetrates into the pores of the base, creating a tacky film that grips the asphalt above. Without it, the binder course might slip or peel away under heavy traffic, a recipe for early failure. The binder course, the asphalt shield. Once the prime coat has cured, the binder course is constructed, usually with dense bituminous macadam, or DBM. This is a hot mix of graded aggregates, filler, and bitumen. The aggregates range from coarse stones about 26.5 millimeters in size down to sand. To fill the tiny voids and improve bonding, mineral fillers such as stone dust, lime, or even a small percentage of cement are added. The binder course is usually at least 75 millimeters thick, and on heavy traffic highways, it may be laid in 2 separate layers, each compacted individually. Grades of bitumen for desert roads. The choice of binder is critical in deserts. VG30, commonly used in moderate climates, softens too quickly above 55 degrees Celsius. So, engineers switch to VG40 in countries like India, Sri Lanka, and Malaysia. In Gulf nations and parts of Africa, the equivalent is 60/70 penetration grade bitumen. Both VG40 and 60/70 pen have higher softening points, above 55 degrees Celsius, which makes them better suited to withstand desert heat. For even greater durability, many desert projects use polymer-modified bitumen, PMB40. Polymers like styrene butadiene styrene, SBS, or crumb rubber are added to the binder. These give asphalt elasticity, So when a truck presses into the pavement on a scorching day, the road can bend slightly and then recover, instead of forming permanent ruts. Temperature control. During mixing and laying, the binder course must be prepared and laid at precise temperatures. The hot mix is produced at 150 to 165 degrees Celsius. Compaction must be completed before the temperature falls below 110 degrees Celsius. If it cools too quickly, air voids get trapped and density is not achieved. If overheated, the binder oxidizes and becomes brittle, leading to cracks. Both mistakes reduce pavement life dramatically. Mix design criteria. To resist rutting and bleeding in deserts, the mix design follows strict limits. Air voids in the compacted mix, 3 to 5%. Voids in mineral aggregate, VMA, minimum 14%. These values ensure that the binder fills the right amount of space, not too little, not too much. The result is a flexible but stable asphalt layer that can handle desert traffic without deformation. So the binder course, supported by its prime coat, becomes the first true asphalt shield against desert heat. It locks the structural layers together, resists rutting at 55 degrees Celsius and above, and prepares the stage for the final layer, the wearing course, which faces the sun, the wind, and the sand every single day. Next, let's move to the wearing course, the road's outer armor and the first line of defense against the desert itself. Layer 5. Wearing course. What keeps the surface safe in the desert sun? If the binder course is the asphalt shield, the wearing course is the outer armor, the layer that vehicles touch every single day. It must survive not only traffic, but also the harshest desert conditions, surface temperatures above 70 degrees Celsius, ultraviolet radiation, abrasion from sandstorms, and oxidative aging from constant sun exposure. The tack coat, ensuring a strong bond. Before placing the wearing course, engineers spray a tack coat over the binder course. This is a very thin layer of bitumen emulsion, applied at 0.2 to 0.4 kilograms per square meter. Its purpose is simple, to create a sticky bond between the binder course and the wearing course. Without this bond, the top layer can peel off or slide under heavy traffic. The wearing course, the final surface. The wearing course itself is usually made of bituminous concrete, BC, or dense bituminous macadam, DBM, designed with high-quality aggregates and durable binders. The thickness depends on traffic. 40 mm for medium traffic, up to 60 mm for desert expressways and freight corridors. Choosing the right bitumen. Ordinary binders like VG30 or VG40 work in moderate climates, but in deserts they are not enough. Here, engineers prefer polymer-modified bitumen, PMB40, which contains polymers such as styrene butadiene styrene, SBS, for elasticity. Or crumb rubber-modified bitumen, CRMB, where finely ground scrap rubber adds flexibility and resistance to cracking. Both PMB and CRMB perform far better under desert heat, helping the surface withstand rutting, bleeding, and thermal cracks. Anti-aging rejuvenators, extending pavement life. Over time, asphalt binder becomes brittle due to oxidation from heat and UV light. To combat this, engineers use anti-aging rejuvenators, special additives that restore flexibility. When reclaimed asphalt pavement, RAP, is reused, rejuvenators are added at about 5 to 12% of the binder weight, depending on the stiffness of the recycled binder. They can also be sprayed directly on the surface as fog seals, sealing microcracks and extending service life. Surface treatments, extra protection against the desert. In some desert highways, an extra layer of protection is added through microsurfacing. This is a thin layer of polymer-modified slurry made of fine aggregates, emulsion, water, and additives. It seals the surface, improves skid resistance, and adds another barrier against sun and sand. Skid resistance, the safety factor. Since this is the layer vehicles interact with directly, maintaining skid resistance is critical for safety. According to IRC standards, IRC 79 and IRC SP 76, A new highway should have a skid resistance value of at least 55, measured by the British pendulum test. Over time, this value may drop, but should not fall below 45. AASHTO guidelines recommend a skid number above 40 for highways, measured using skid trailers at 40 miles per hour. To meet these values, engineers use angular, hard aggregates with low water absorption. Rounded river gravel is avoided because it polishes under traffic and reduces grip. So the wearing course is not just a black top coat of asphalt. It is a carefully engineered armor, built with modified binders, rejuvenators, angular aggregates, and protective surface treatments. Supported by the tack coat beneath, it ensures that desert highways remain safe, smooth, and durable, even under the punishing sun and the constant attack of wind-blown sand. But remember, the desert doesn't stop at the road surface. It keeps attacking from the sides with sandstorms and from below with flash floods. That's why the next chapter is all about sand and flood protection measures, how engineers stop the desert itself from swallowing highways. Sand and flood control. How do engineers stop the desert from swallowing roads? A desert highway doesn't just battle the scorching sun above. It is also constantly attacked from the sides by shifting sand, and from below by sudden flash floods. Left unprotected, dunes can bury lanes overnight, and floods can wash away embankments in a matter of hours. So how do engineers keep these roads alive in such a hostile environment? Sand encroachment and wind control. The first enemy is shifting sand. Strong desert winds carry sand grains across highways, reducing skid resistance, covering markings, and sometimes burying entire stretches of road. To fight this, engineers use wind barriers and sand fences along the highway. These simple structures reduce wind speed near the ground, forcing sand to drop before it reaches the pavement. In countries like the UAE and Saudi Arabia, highways often include sand trap zones, narrow strips beside the road with low concrete ribs or barriers. These act like catch basins, capturing sand before it piles onto the road surface. Another strategy is vegetative screening. Drought-resistant plants like tamarix or prosopis are planted along road shoulders. Their roots stabilize the soil, while their canopies slow down surface winds. Finally, many desert roads are built slightly elevated above the natural ground. The side slopes are protected with stone pitching, layers of tightly packed angular stones that resist erosion and prevent dunes from climbing up onto the road. Surface protection against wind erosion. Even the road surface itself can be attacked by wind-driven sand. To reduce erosion, engineers sometimes apply bitumen seal coats or emulsions. These treatments bind the top particles together, making it harder for winds to strip them away. Protection against flash floods. The second great enemy of desert roads is water, in the form of sudden flash floods. Although deserts look dry, storms in distant mountains can send torrents of water crashing through dry riverbeds, called wadis. In just hours, these floods can tear through embankments and destroy pavements. To prevent such damage, highways are equipped with drainage channels to guide water away, culverts and pipe drains under the embankments, and causeways or low-level floodways where water can safely pass over the road without destroying it. In Oman, where highways frequently cross wadis, engineers build reinforced concrete floodways, low-level concrete beds that allow floodwaters to flow across the road surface. For smaller flows, culverts are embedded beneath, ensuring continuous drainage when floods are absent. Embankments are further protected with stone pitching or gabion walls, wire mesh cages filled with stone. Gabions act like flexible retaining walls, absorbing the force of water while preventing soil erosion. Similar solutions are used in Saudi Arabia, the UAE, Jordan, and North African desert regions, where flash floods are a constant hazard. So protecting a desert road is not just about building the pavement strong. It is about designing defenses against two powerful enemies, the sand that buries highways and the floods that wash them away. But deserts are also becoming test labs for new solutions. In the next section, we'll explore modern technologies like solar reflective coatings, plastic-modified asphalt, and drone-based inspections that are making desert highways smarter and more durable than ever before. What are the latest technologies for desert road durability? Deserts are some of the harshest testing grounds for pavements. But they are also becoming innovation laboratories, where engineers experiment with new technologies to make highways last longer, perform better, and even become more sustainable. So, what are the latest breakthroughs shaping desert highways today? Solar reflective coatings, cooling the pavement. One of the most promising technologies is solar reflective coatings. These are special paints or surface treatments that reflect sunlight instead of absorbing it. By doing so, they reduce the road's surface temperature by 10 to 20 degrees Celsius. In Rajasthan, India, trials showed that reflective coatings increase pavement life by up to 25%. Lower surface temperatures mean less rutting, less bleeding, and slower oxidation of the bitumen. In desert climates where asphalt can reach 70 degrees Celsius or more, this small reduction makes a huge difference. Cold mix asphalt, repairing roads without heat. Another technology gaining attention is cold mix asphalt. Instead of heating bitumen to high temperatures, engineers use bitumen emulsions that can be mixed with aggregates at normal room temperature. Why does this matter in deserts? Because transporting hot mix over long distances in remote desert areas is difficult. It often cools before it arrives. Cold mix asphalt allows repairs to be done on site, quickly and efficiently, even far from hot mix plants. It also saves fuel, reduces emissions, and is safer for workers. Recycled plastic waste in asphalt, turning waste into strength. Many desert countries, including India and the UAE, are now using recycled plastic waste in asphalt mixes. Shredded plastic is heated and blended with bitumen, where it coats the aggregates and improves bonding. The benefits are twofold. It provides a sustainable way to reuse waste plastic. It makes the asphalt more flexible and resistant to cracking under extreme desert temperatures. Roads built with plastic-modified asphalt have already shown better performance in resisting rutting and surface damage in hot climates. Thermoplastic sealants, flexible crack repair. Even the best desert roads eventually develop cracks due to thermal expansion and contraction. Traditional bitumen sealants often fail because they harden and break under desert heat. The solution? Thermoplastic sealants. These remain flexible even at high temperatures, expanding and contracting with the pavement. This makes crack repairs longer lasting and reduces the need for frequent maintenance. Drone-based inspection and monitoring, smarter maintenance. Finally, technology is not just changing road materials, but also how roads are monitored. Drone-based inspection systems are now being used on desert highways. With high-resolution cameras and thermal sensors, drones can scan long stretches of road in minutes. They detect cracks, sand accumulation, drainage blockages, and even hot spots where the asphalt is overheating. This allows engineers to plan preventive maintenance before problems become severe, saving both time and money. So desert road technology is no longer limited to just thicker asphalt or stronger binders. It now includes cooling coatings, cold mixes, plastic-modified asphalt, thermoplastic sealants, and drone-based inspections. Together, these innovations are making desert roads smarter, stronger, and more sustainable than ever before. But even with the best technology, timing is everything. In deserts, laying asphalt or concrete at the wrong time of day can ruin an entire project. That's why in the next section, we'll uncover the right time and method to build pavements in desert climates. What is the right time and method to lay asphalt in the desert? In desert climates, even the best designed asphalt mix can fail if it is laid at the wrong time of day. Here, timing is not just important, it is everything. Why? Because the desert sun cools asphalt too fast and leaves no time for proper compaction. So when is the right time to pave a desert highway? The golden rule is simple: work during the cooler hours. Paving is scheduled before 10 in the morning or after 5 in the evening, when surface temperatures are lower and winds are calmer. The asphalt mix is delivered at 150 to 165 degrees Celsius. Once laid, it must be compacted while still hot, ideally within 10 to 12 minutes. If compaction is delayed, the mix stiffens, density is lost, and dangerous air voids remain inside the pavement. Both IRC and AASHTO standards highlight these timing and temperature limits because ignoring them leads to rutting, bleeding, or early thermal cracking. So the secret is not just in the materials chosen, but in when and how they are placed. By paving during cooler hours and following strict temperature controls, engineers give desert roads the best chance to survive the harsh climate. But even the best laid asphalt won't last forever. That's why in the next section, we'll explore the maintenance practices that keep desert highways safe and reliable year after year. Case studies and conclusion. What can we learn from desert road engineering? Building roads in deserts is not just about construction. It is about engineering innovation, where every decision, from binder grade to sand control, is designed to fight nature's extremes. Let's look at a few real-world examples. In Dubai, highways are exposed to surface temperatures above 70 degrees Celsius. Engineers use polymer-modified binders, advanced drainage, and sand control systems to keep these roads safe and smooth, even in summer heat. In Namibia, where weak desert sands make construction difficult, roads are stabilized using geocells and chemical treatments. These allow highways to carry heavy trucks through some of the harshest desert landscapes in Africa. And in the Nevada desert of the United States, engineers are adopting solar reflective coatings and drone-based monitoring to reduce pavement temperatures and identify failures early. These technologies extend the life of pavements in a climate where both heat and traffic are unforgiving. These examples prove that desert road engineering is not just theory. It is a living practice, a field where science, materials, and creativity come together to build infrastructure that survives against the odds. So what can we learn from all this? That every challenge, from heat-softened bitumen to shifting sand to sudden floods, has a solution. High-temperature binders resist rutting. Geosynthetics stabilize weak sands. Rejuvenators extend asphalt life. And modern technologies, from reflective coatings to thermoplastic sealants, push desert highways to last longer and perform better. And yet, deserts are just one type of extreme climate. In our next episode, we'll explore the opposite challenge, constructing roads in rainy and flood-prone areas where water, not heat, becomes the greatest enemy of pavements. Don't forget to subscribe to Civil Guru Solutions and share this video with your fellow engineers, students, and professionals. Together, let's continue building smarter, stronger infrastructure, one layer at a time.